All right, so I wanted to work through this example for you guys. We're asked to consider the set of vectors S here. And first, determine whether the vector 0, 5, 5 is a linear combination of those vectors in S. So it's good to work these problems using just an understanding of the terms here instead of just, it's easy to kind of slap down an augmented matrix to kind of guess the right way to set it up and row reduce without really understanding the connection between the matrix you're writing and the actual words in the problem. So I want to work off of that. Linear combination. So that refers to a combination of scalar multiples of these vectors. So let me work part A down here, I guess. That refers to something like S1 for scalar number 1 here times this first vector in S here, plus some scalar multiple of the second vector, plus some scalar multiple of the third, equals, so if V is a linear combination of these vectors, then there should be scalars S1, S2, S3, where I can combine the vectors in S in this way and generate the vector 0, 5, 5. If we can do this, then 0, 5, 5 is a linear combination of the vectors in S. So here we've got a vector equation. Now in this section, there's a discussion of why exactly a vector equation of this form would be equivalent to the augmented matrix with these vectors in S as the columns, augmented with this 0, 5, 5. For a little bit of background on how I get from here to here, I would set up a system of equations. So I would take this equation here, and let's say we actually do the arithmetic on the left side here. So we do S1 times each entry in this first vector, S2 times each entry here, and then S3 times each entry here. And then take the sum of all of those terms. And so what I would get is negative 1 times S1 plus 1 times S2, and then plus negative 2 times S3. And then in the second entry, I would have 3 times S1 plus 2 times S2, which I'm getting from here, plus 11 times S3. And then third entry, I'd have 4 times S1, S2 times 1, 13 times S3. Okay, equals this vector 0, 5, 5. So that would lead me to this system of equations. All right, well then this first entry here must equal 0. Second entry here must equal 5. And then third entry must equal 5. That system of equations right there is represented by this augmented matrix. First row is negative 1, 1, negative 2. There's your coefficients from this first equation, equals 0. And then 3s1 plus 2s2 plus 11s3, there's your coefficients, equals 5, and so on. Okay, so that's the connection, but we don't want to write out all of those steps every time. We don't want to write the vector equation and then the linear equations and then the augmented matrix. So we do start to accept, okay, so this vector equation is equivalent to this augmented matrix. Now we want to try and solve this thing. Remember that your pivots don't have to be 1. So if you want to multiply negative 1 times row 1, that's fine. You can do that. It's perfectly legal. You don't have to, though. So I might just do 3 times row 1 plus row 2 right now, because 3 times row 1, so that'd be negative 3 plus 3. That would get a 0 in this position. So let's see. So 3 times row 1. So like I said, that'd be negative 3 plus 3, and then 3 plus 2, and then negative 6 plus 11, and then 0 plus 5. Now I'm going to stack a second operation here. I want to also get a 0 in this position. So I'm going to do 4 times row 1 plus row 3. That's an independent operation, so it's not affected by this previous step here. So I can get away with kind of doing both of those at the same time. So that'd be negative 4 plus 4, and then 4 times this. So 4 plus 1, and then 4 times this. So negative 8 plus 13, and then 0 plus 5. Whenever you get two rows that are exactly the same like this, you're going to end up with a row that's all zeros. And actually, whenever you have one row that's a multiple across the board of another row, then that row is going to clear out. You're going to end up with all zeros. I'm trying to see where I can... Oh, I can do that. So I'm going to do negative row 2 plus row 3. That's going to clear out row 3. So you have 0 plus 0, negative 5 plus 5, negative 5 plus 5, negative 5 plus 5. There you go. And then the obvious next thing would probably be to take 1/5 of row 2, since those are all 5s. Okay, now at this point I could answer the first question. Is this vector a linear combination? Well, that's just a matter of, can I find scalars S1, S2, S3 that satisfy this equation? So in other words, does this matrix represent a consistent system? Is there any solution at all? And so the answer here is yes. We can see this thing is now in it's now in echelon form. We have pivots here and here. Pivot by definition is the first non-zero entry in each row. There is no pivot in row 3 here, and there is no pivot in column 3. But as long as you do not have a pivot in the very last column, which we will not have that, then the system is consistent, which means yes, we can find scalars S1, S2, S3 that satisfy that equation. In fact, because there is no pivot in column 3 here, because we have a non-pivot column, that indicates that this system has a free variable. And whenever your system has a free variable, that indicates infinitely many solutions. So answer to this first question is yes. 0, 5, 5 is a linear combination of those vectors. Second part is saying, okay, so if it is, then express it as a linear combination. So that's actually asking us to solve for S1, S2, S3. When a system has infinitely many solutions like this one does, I tend to prefer to reduce all the way to the reduced echelon form. So this thing is now in regular row echelon form. I want to get it all the way to the reduced. And this is a personal preference here. You could switch to a system of equations from here and come up with a solution. But I'm going to work my way all the way to the reduced echelon form. And I only need one more operation to do that. To get this thing in the reduced echelon form, I just need to get... So, well, okay. Technically, I got to do two things. For something to be in reduced echelon form, there's two added criteria. So it's all the criteria for echelon form with the two additional requirements that this time your pivots do actually have to be ones. So I'll get a 1 in this position, positive 1. And where every column that has a pivot, that pivot should be the only non-zero entry in that column. So, I mean, like column 1 would be okay as far as that requirement goes. But column 2, if there's a pivot here in row 2, I need to get rid of that 1 right there. So let me take care of those two things. I'm going to first do negative 1 times row 1 to turn this pivot into a positive 1. So that'll make this a negative 1. This will be positive 2. 0, still 0. Okay. Then I want to get a 0 in this position right here. And so I can do that by taking row 2 plus row 1. That's going to be the new row 1. So that'd be 0 plus 1, 1 plus negative 1, 1 plus 2, and then 0 plus 1. Now that I have it in the reduced echelon form, I'm going to write the corresponding equations. So remember, our unknowns were S1, S2, S3. So this first row set tells me S1 plus 3S3 equals 1. The convention is that you solve for your leading variable. So solve for S1 in this case is equal to 1 minus 3S3. The second row tells us that S2 plus S3, this should be a 3, equals 1. Solve for the leading variable, so S2 equals 1 minus S3, and S3 is a free variable. So we can let S3 equal whatever we want. So as far as coming up with a solution, everybody could come up with a different solution and we'd all be right. So just as an example, suppose we let S3 equal 1. Then S1 will be 1 minus 3 times 1, 3 times S3. So 1 minus 3, that'll be negative 2. And S2, trying to slide this down, here we go, would be 1 minus S3, so that's going to be 1 minus 1, so 0. And S3, like I said before, I'm letting that equal 1. So one possible solution out of the infinitely many is to take, okay, S1 is negative 2 times the first vector, plus S2 is 0 times the second vector, plus 1 times the third vector, and that should generate that vector 0, 5, 5. But so with these problems, it is pretty straightforward as far as how to check your answer. Let me just fill in these vectors we were given that I've forgotten. So it's negative 1, 3, 4. And then this second vector doesn't even matter since we're multiplying it by 0, but I'm going to fill it in just for completeness here. And then third one, what was the third vector? Negative 2, 11, 13. Negative 2, 11, 13. And let's just see if this works. I'll get the highlighter, it's easier for me to point. So negative 2 times negative 1, so that'd be 2 plus 0 minus 2 would give us 0. That looks good. Negative 6 plus 0 plus 11 would be positive 5. That's good. And then negative 8 plus 0 plus 13, that would be positive 5. Yes, so this does seem to work. If you were thinking let S3 equal 0, by the way, if S3 is 0, then S1 is 1, S2 is 1. And let me just point out, yes, 1 times the first vector, this one, plus 1 times the second vector. If you add those together, you'd get 0, 5, 5. So that's another solution. And like I said, there's infinitely many there. But so I get questions like, well, I don't understand what the second part, if so, expressed as a linear combination on that part A. Sometimes people don't understand exactly what they're being asked for. This is the sort of thing you're being asked for. Here's where I have expressed 0, 5, 5 as a linear combination, scalar multiple, sum of scalar multiples of the given vectors. So that's your answer to A. I'm going to go ahead and answer B in this. Actually, I'm going to go ahead and end this video and make a separate video for part B.